Good morning. Today is the 9th of April, excuse me, 2026. This is the BEL second semester mathematics lecture. And today we start with logistics replenishment dynamics with Laplace. So we see problems like page stock, reorder point, Kanban, conwip, or conwip means constant work in progress, or economic order quantity, EOQ, from a mathematical perspective. We are going to get some notation first, just as always, so that we know what we're talking about. I of t, it's going to be the inventory deviation. Or stock deviation. B of t is going to be the backlog. W of t is going to be the work in progress, inventory that is in progress, or work in process. Okay, work in progress or work in process. In America, they say work in progress. In Europe, work in process. D of t is demand, or withdrawal rate, the speed at which I get material or products out of the shelf. Q of t is the replenishment. Rate, the speed at which I fill in the shelves. R of t is the release rate. C of t is the completion rate. This is going to serve to solve some problems. I star, W star are going to be target values, and U of t is the step function. Okay, so some usual problems. So the core state balances in logistics are going to be 3. Okay, the first one is going to be the inventory. The rate at which inventory changes, the speed at which inventory changes, is Q minus D. Okay, Q is the replenishment, and this is very logical. The replenishment, I'm filling the shelf at a certain speed. This is the replenishment rate, and I am emptying the shelf at a certain speed. And here in the middle I have the inventory balance. Okay, this should be something that you have ingrained in your minds. It's very important. Other balance that is important is the backlog balance. Okay, which is the inverse. Backlog balance is D of t minus Q of t. Okay, so the other way around is I'm looking at the demand, what I'm taking off the shelf, and what I'm filling. Basically the same as the inventory balance, but with a minus before. And the third one is the work in process, or VIP. Okay, we call also WIP. working process, which is going to be W with a point. The first derivative is going to be the release rate minus the completion rate. Okay, so if I have let's say a machine or a process step, I release the products. I release the products in, and I complete them at a certain date, and that rate is going to be the work in process or work in progress. All right, so these are the 3 problems we are going to look at in detail. All right, any questions so far? Okay, so let's look at the base stock and reorder point. As feedback loops. We have, so from a mathematical perspective, so let I of t be the inventory deviation from the desired level. We use a proportional replenishment rule and this is going to be Q of t. Q, remember, is the replenishment rate. How do we fill in the shelves? It's going to be equal to K, proportional, okay, to the difference between the target inventory minus the real inventory, okay? So this is the replenishment rate. The replenishment rate is proportional with K to the inventory delta, okay? What should be minus what is. This is the way to interpret it. If inventory is below target, then the target I will start minus the real is bigger than 0. So replenishment is increased. Okay. If we combine this equation, the replenishment rule, with the inventory balance, we saw above, which states that the inventory rate equals Q minus D, then and we insert the policy, then we have that I with a star, with a point, the first derivative, equals K I star target inventory minus I of T minus D of T. Okay? And therefore, I of T, the first derivative, plus K I of T equals the proportional times the target inventory minus D of T. Okay? This is the dynamic replenishment equation. Okay? Is that cool? Any questions? This is the general dynamic replenishment equation. So now if there is no demand disturbances, then D of T equals 0. Then this is a special case, I plus Ki equals Ki target. We implement Laplace. Well, I guess this is better to write it in the time domain. Excuse me, let me write it again. Laplace transform tells us this is Si of S plus Ki of S equals Ki target of S. This is with 0 initial conditions. As we have seen, we need to subtract the initial conditions, but we make our lives easier now. So result we get that the I of S divided by the target equals K S plus K. Okay. So this is the transfer function. How many times? Remember what we saw yesterday, how many times the actual inventory is contained in the target inventory. Okay? So now suppose there is a step target change. Okay, so imagine that our target changes some delta, some step, and then with a step function. Yeah. Any questions? Do you have any questions? I can hear you. Okay, if you have questions, please put your microphone on and then just ask. Then I of s star equals some quantity that we have increased divided by s. Okay. So as a result, what we're getting is that I of s equals k divided by s plus k times some delta divided by s. Okay. If we solve this, we get that this is delta E star delta E star, so the increase of the inventory target, 1 divided by 1 plus s divided by k. And if we invert or use the Laplace inverse, transform, we get that IoT equals the increase on demand 1 minus e to the potent of minus kt. Okay. All right. Any questions? So in as a result, if we get with this replenishment rule, if we get a demand an inventory target increase, that is step function, okay, so if from t equals 0, the inventory target increase is some delta I star, okay, this is I star of t, then we know that with this replenishment rule we have depicted, the I of t will behave the following way. For t equal 0, I will have 0, okay, and for t equal infinite, I will have the same level of increase in the target. So the system will adjust towards the target following such curve. Okay. Good. Which is somehow logic. So this is the standard. First order adjustment of inventory. Excuse me. Okay. So now what happens if we have a demand rate disturbance? Remember above we said that demand is 0, okay, here. What happens if we have demand response disturbance? We have still the same equation. Minus d. With a target, with a constant target. So what we get is this equation. If we go ahead and say, okay, this is going to be, wait, this is in the time domain. We have, we apply Laplace. So we have I of s divided by d of s equals minus 1 divided by s plus k. We have a demand step again. So d of t is some demand step times the unit equation. So d of s equals some demand step divided by s. As a result, we get, if we plug that in above, we have that I of s equals minus delta D, the demand step, divided by S times S plus K. And as a result, hence the inventory time equation is minus delta D divided by K, 1 minus E minus KT. Okay. And this is very useful in logistics, super useful, super duper useful. Logistics interpretation a sudden increase in demand, let's say delta D, causes an inventory drop. Okay. So let's visualize this. If we have a sudden increase in demand, let's say if in t equals 0, our demand increases. Sorry, let me get a different color. Our demand increases some delta D, sorry. Then automatically our inventory is going to drop. If the target inventory is not touched, automatically our inventory is going to drop. Some value, okay? So if this is I of t, our initial condition is going to be for t equals 0 being 0, okay, from the initial condition, whatever the inventory is, and for the for t infinite is going to be minus delta D divided by K, so inventory is going to drop this amount. Okay, so if the customer suddenly asks for more, we need to be prepared because the inventory is going to drop. Okay, makes sense? Important for you is that a larger replenishment gain reduces the long run deviation. If K is big, then delta D minus delta t divided by k is small. Okay. Okay. So a larger k speeds up the correction. All right. Any questions? Okay, so we have seen now the demand disturbance response. And a proportional base stock and viewer point with a proportional replenishment rule. Now let's look at Kanban. So Kanban will be a topic that you will see in many other lectures, okay? If you don't know it yet, it's about, it follows following logic. You withdraw some yogurt from the shelf. This triggers a replenishment signal. When you go ahead and pay, this triggers a signal to replenish or produce. And then the stock is being refilled. This way the stock is never empty. Okay, it's a super simple way to the key point, and let me paint here my superhero H4 to remind you of the importance of this. The key point here is that replenishment does not occur instantly. Okay, there is a lead time. This is realistic when you go to buy some yogurt at I don't know, some store. You take the yogurt and it's not replenished instantly. When you buy some car, the car is not replenished instantly. Okay, so we model the lag as a first order response of the replenishment rate Q of t to the withdrawal demand d of t. So the Kanban lag model. Kanban is a Japanese word meaning it's written like this. In hiragana. Kanban lag model, it means card. Okay, the Kanban lag model is some time response, tau, the first derivative of the replenishment response rate plus the response rate equals the demand. Okay. Tau sub k is an effective replenishment time constant. So it's actually defining how the system in the Kanban loop is reacting. So we apply Laplace to this equation. We get tau sub k times s q of s plus q of s equals d of s. Okay. So what we get is that q of s divided by d of s equals 1 divided by tau sub k s plus 1. But we saw in the inventory balance that at the beginning of the lecture that the inventory change equals q minus d. So what we get is that I of s equals q of s minus d of s if we implement Laplace. Okay. So if we put these two together, and whenever we find q, we put d of s divided by tau ks plus 1. We find that I of s equals q. This is d of s divided by tau ks plus 1 minus d of s divided by s. I've just put here in this part. Okay. So as a result, we get that the transfer function of the inventory and the demand equals 1 divided by tau sub k s plus 1 minus 1 divided by s. So if we transform this a little bit, this turns out to be 1 minus tau sub k s plus 1 divided by s times tau sub k s plus 1 . This is minus tau sub k s divided by s times tau sub k s plus 1. This equals minus tau sub k a divided by tau sub k s plus 1. Okay, this is our transfer function in the Kanban loop. If we have a step increase, in the withdrawal, some customer comes and takes 10 yogurts at a time. Okay, so suppose d of t equals some step increase, just as before. Then we can say that d of s, applying Laplace, equals delta d divided by s. So what we would be getting is I of s minus tau k divided by tau k s plus 1 times delta d divided by s, and applying inverse Laplace, we get that I of t equals minus tau k delta d 1 minus e minus d divided by tau k. And this has a very meaningful result. Okay, this is the way the inventory changes with a step demand increase in a Kanban described as above. Okay, so a sudden increase in demand consumes stock during the replenishment delay. Okay. The final inventory loss is this tau sub k times delta d. Okay, so if tau sub k is very high, the replenishment time or the response time is very high, then it takes longer to replenish, and then we lose more inventory. Okay. Any questions? So we have seen Kanban. In the Kanban rule, there is a trigger of replenishment signal once we withdraw. Okay. Now, but Kanban has the problem that it's difficult to implement. That's why engineers have looked at a different way that is easier to implement. It's conwip. It's called constant work in progress or work in process. This way of acting is conceptually a little bit different. Okay, this push-pull concept. In conwip, there is a limit in WIP, work in progress, work in process, for the whole process. Okay. Once this limit has been reached, so we are below this work in progress, withdrawal signal is triggered. The goal here is to keep inventory work in progress constant. Okay. So whereas in Kanban, we every time we take one yogurt off the shelf, there is a signal. With conwip, there is only one signal if there are less than 10 yogurts in the shelf. Okay. So the state balance is like this: W the work in progress rate is equals R of t minus C of t. Remember, R small is a release rate and C is a completion rate, as we saw above, and we are going to use a release rule. R of t equals the completion plus some proportional target minus actual value. Okay, again, a linear matter. And here is exactly the same game as above. We insert this into each other. So W t is C of t plus k okay, so what we get is that W of t equals k W star minus W. We apply Laplace again. Ws multiplies s plus k equal W star s times k. So we get the transfer function for the work in progress k divided by s plus k. And this is our transfer function for the conwhip in first order. So for step response, in the target, so that this is true, what we get is that I mean, it's the same math as above. After applying our Laplace inverse transform, some delta, and then 1 minus e to minus kt. Okay. So the ideal conwhip regulation is linear of first order whip regulation loop. Okay. And this is an important takeaway. All right. So, any questions? No. So then another important issue here, or another important concept, is called Little's law. I put this in big capital letters. This is very important, okay? In fact, this is the most important equation that you will see in logistics ever. Little's law states that work in progress is equal to throughput times cycle time. I write it again. Work in progress or work in process equals throughput. Can you please switch off your sound if you're not going to ask questions? Thank you. So this is true for any process. Okay. And this is a very hard assumption. Whenever you have a process, let's say, paint here a factory, the working process, the inventory that you have in the process equals the throughput. Throughput is measured in parts per time unit. Working process is measured in parts. And the cycle time is, of course, measured in time. Equals the throughput times the cycle time, how often you bring out one part. Okay. This means that cycle time equals the working process divided by the throughput. Okay, this is immediate. Or the throughput equals the working process divided by the cycle time. This is the same, okay? Super important rule for your life as logistics experts. One book you should read, you must read it. It's not part of this course, okay? But one book you must read. Ask Santa to bring it next Christmas. And I'm not asking you to read it. You must read it, okay? It's called Factory Physics. Factory Physics, I think the authors are Sperman and Hobbs. Yeah, Hobb and Sperman. If you are going to read one book in your life as logistics, is this book. As logistics experts, is this book. Okay? If you understand this book, you will understand process management, you will understand the physics of a factory, of how processes work. Read it no matter what. Okay? Good. Well then, I'm going to stop the video here.